I'm the last speaker, and I would like to give a little bit light talk. So this is also Blackboard talk and not so many technical details, but I hope that you can follow me and you will still have energy to follow this last talk. So it joins to some of the talks which were this week about Q goes to zero limit or Q goes to infinity limit, crystal limit. You know, you heard these things. I will be talking about large coupling limit of certain interacting spin chains. And you know, the large coupling limit of XYZ spin chain is the same as this crystal limit. But I will be talking the same thing from a little bit different point of view. And in fact, I will actually introduce a new integrable model, which was, well, introduced in the last 2 or 3 years. And hopefully I can discuss some of the properties of this model. But first about motivation. So why do we do this? So I will talk about large coupling limit of certain integrable spin chains, XYZ and Hubbard if I have time. But also I can join to the previous talk of Oleg, namely people are looking at time evolution, non-equilibrium dynamics time evolution in certain quantum integrable models. And you know that if you have non-equilibrium, if you have real-time evolution, then everything is very difficult, much more difficult than normally in beta ansatz or normal techniques of integrability. Because this beta ansatz is very well suited to study eigenstates, eigenenergies, or ground state, or maybe some correlation functions or entanglement in ground state or things like that. Most of the talks that you heard, for example, this week were also something about ground state and these kind of things. As soon as you start real-time evolution from a non-equilibrium, some state which is not an eigenstate, then you excite all of the states in your spectrum and you need to deal with all of them. And somehow all of the things become very, very complicated. And people want to look at these types of problems because they are doing transport. They are investigating transport in integrable models, transport of conserved quantities, and things like generalized hydrodynamics, peer and ballistic transport, diffusive transport, even more exotic types of transport properties or behaviors appear. So then I will continue. And so real-time evolution is difficult. And then what people can do is not much for a generic system. So for a general Heisenberg spin chain, they cannot do much with rigorous methods, with exact analytic methods. Instead, what people do is they try to select toy models. So some simple models which have simpler interaction than the normal Heisenberg spin chain, which is still too complicated. And one of the possibilities for selecting a toy model is to take a known model and then you do a large coupling limit. And then you hope that in the end, your model, what you get in the end is non-trivial, but simple. And this is what we will do now. Yeah, let me start directly with the models. And actually, most of the talk will be about Heisenberg spin chain. And I will then start here with the Hamiltonian of the Heisenberg spin chain. So I will use a notation where I denote Pauli matrices by X, Y, and Z. So I will not write sigma X, it's just too many letters. So Pauli matrix X, Y, and Z. And then the Hamiltonian is the following. You know it very well, but I need to write it down. Summation over sides, the Pauli matrix XX plus YY. So this is a J plus 1, J plus 1 plus some delta parameter times Z, J plus 1. This is Hamiltonian of Heisenberg spin chain. And I want to look at the delta infinity limit. And then you can ask yourself, I mean, how is this not trivial? So what will this guy talk about? Because of course, this is a trivial limit and it has been investigated many, many times in the literature, certain different types of the limit. So I want to tell you that hopefully what I tell you now is actually new. You will see, but I need to explain to you in what sense I'm investigating in this limit. Because trivially, if you just take Q2, new operator Q2, where I select this term, so I will just write Q2 is summation over J. Then clearly when you send delta to infinity, plus infinity or minus infinity, then this Q2 will dominate within Hamiltonian. And this can be diagonalized easily. And this is what we could call maybe the classical Ising model, if you want. So these are summations over the sums of mutually commuting operators. You know, eigenvalue of this is +1 or -1. So the value of this operator is trivially just some integer, which is sums of +1 and -1. The values are here +1 if you have a configuration on neighboring site, which is the same spin configuration, up, or down. Then you get a +1, and you get a -1 when you have something like a domain wall. So either you have down, up, or you have the, and the sum is an integer. And then this will dominate here. And then somehow you would think that this is completely trivial. So delta infinity limit is given just by this one, and we solve the model, no? Okay. I will tell you that what we need to do to get something non-trivial. But first, again, if we want to look at ground state, for example, ground state energy or ground state properties, and then we look at the delta infinity limit, then it is indeed completely trivial. Because in the ground state, it is true what I said, that only this remains, this will dominate. And the ground state of this guy is very simple. If delta is positive, goes to positive infinity, then we have the antiferromagnetic case, then the ground state will be given by the near state. So where you have up, down, etc. And there are two degenerate states. If delta goes to minus infinity, then the ground state, then this is ferromagnetic, and the ground state of this one will be all spins up or all spins down. And it's completely trivial. There's nothing happening. So in order to get something non-trivial in this model, we need to forget about the ground state, and we need to look really for non-equilibrium situations, something where we excite all of the parts of the spectrum. And for this thing, what I will do is I will actually compute, well, not compute, but consider spin transport. So, you know, there are the spin Z operators, which is a conserved quantity. Maybe I should actually write it down before I forget. So there is also a conserved charge. Well, there's a conserved charge. I call it Q1, which is summation over Z, sigma Z operators. And then we can look at transport of these local quantities, the local spin operators. So I want to compute a correlation function, or at least consider a correlation function like Z at site 0 at time 0 multiplied by Z at site J at time T, where I understand that this is Heisenberg equation of motion, real-time evolution for the operator sigma Z or SZ, and I compute the mean value in some finite temperature ensemble. So I can define a finite temperature ensemble with the standard formulas. And once I do this, then immediately I excite all parts of the spectrum, because this is clearly not ground state. And then somehow we want to find the limit where we can combine this limit, delta to plus infinity or actually minus infinity, with something here for this correlation function such that it becomes meaningful and non-trivial and non-zero. And then what we do is actually a combination of infinite temperature limit combined with this large coupling delta limit. Actually, how should I introduce it? Let's do it. I will first tell you the definition of what I want to do, and afterwards I give you motivation why I want to do this. So I want to do a limit where I set temperature to be much larger than the delta, but I also set delta to be much larger than 1. So this is a combined limit. I mean, if you wish, I can set temperature to delta square if you want, or something like this. But it doesn't matter. I mean, how it scales, it must be much bigger than delta. And then my statement is that then this becomes an average, where basically I average, it's practically an infinite temperature average, where I average over all parts of the Hilbert space. And then somehow the really crazy things which normally would happen for this operator, that we focus on either the near state or the ferromagnetic states, they don't happen anymore, because we have such big temperatures that all parts of the spectrum contribute. And then we can look for non-trivial dynamics. And first, here you can have a critique that this is a crazy limit. Why would you look at this? No, I mean, maybe it's not physical. I can tell you why we look at this, then you can believe me that it is important. We look at this because in generalized hydrodynamics, people look at transport properties like this, and they compute the large time and large distance behavior of this object. So they look when the distance between the two operators goes to infinity, and also time goes to infinity. And then they look at different behavior for this object. It can be ballistic transport, diffusive transport, depending on what model you consider, which regime you consider, etc., etc. And then they have, from generalized hydrodynamics, they have predictions. So in ballistic case, they have predictions for so-called Drude weight, what gives you ballistic transport. In the diffusive case, they have prediction for diffusion constant, of spin diffusion constant. And you would want to check this. So generalized hydrodynamics is a little bit phenomenological theory. It is developed for integrable models, but there are many, many assumptions meanwhile. And it's not a derivation from first principles. So maybe you would want to check these derivations, or provide the derivations. And this is what we do. And then in this case, this special limit is actually convenient. This is convenient because in hydrodynamics, they actually have a prediction for this limit. And then it turns out that in this limit, the prediction is from hydrodynamics that this is a diffusive diffusive transport, and then there is a well-defined spin diffusion constant, and it was calculated to be actually a number which is given in papers. The spin diffusion constant is 4/3 pi. It's a number. Volume of the square by some volume of the sphere by some accident. But anyway, this is a number which is given by hydrodynamics, and maybe you want to prove it. So at the moment, we don't have a proof of this, but I'm just telling you that this gives a motivation to study this crazy limit, okay? Because if we study this crazy limit, then maybe we can, in this crazy limit, we can do computations which is truly rigorous, analytic, and eventually we might be able to prove this. Actually, we are close to this, but we don't have this one yet. But we have many steps from this project. All right. So now I explained what I want to do, and then let us go back really to the Hamiltonian with this assumption that we take infinite temperature average so that we compute all of the states in the spectrum. We take them, all of them, into account. So then we need to think a little bit, what does this Hamiltonian actually do? So what is the effect of these terms when we have this guy also here and send delta to infinity? And for this one, I will draw a figure. Maybe I will draw a figure first here. So imagine that we draw the spectrum energy levels simply for some finite volume. So we set finite volume, I don't know, L to be, I don't know, 8, 10 or something. Then you know that the eigenvalues of this Q2, they will be integers, but they will not be very big. I mean, I don't know, it goes from minus L to L or something. But then delta is large, so the spectrum will be somehow separated according to these I call them sectors. It's not a true sector yet, but the spectrum will be somehow concentrated around the eigenvalues of this Q2, where these separations will be, I think, they will be something like 2 delta. So there will be many states in close of these integer energy levels. I mean, multiplied after they get multiplied by 2 delta. And then there will be these small differences here. And the small differences arise somehow from the effect of these guys, because they are still there in the Hamiltonian. So this will become dominant, but there are still these small changes which give you some states which are centered around some value given by the integer Q2. And as you increase delta, then they really become sectors which don't communicate with each other. When I say this, it's not rigorous. It's just, again, for this talk, I'm giving you phenomenological arguments. But please believe me that this computation, what I'm about to show you, this can be done rigorously. I just don't want to tell you now the rigorous derivation because it just, well, I think it's less understandable. I want to tell you some story which is perhaps, hopefully, understandable. So if you increase delta, then these states will become very far from each other in energy. And then effectively, it will mean that states which belong to different sectors, they will not communicate with each other. And somehow the only effect that we need to care about is the effect of this XX and Y perturbation, so to say, within each of these sectors. I can also tell it in a different way. Thanks for that. I will just mention domain walls in a second, but good, thank you. And what did I want to say at this point? So yeah, and you can also understand this kind of separation into sectors by looking at this correlation function. Try to do this. What is this spectral expansion also what Oleg had, and then you will see that if you have transition matrix elements which include 2 states from different sectors, then there will be a big large energy difference and very quickly oscillating phases, so they will drop out eventually. They will average out very quickly, and for this guy you only need to keep transition matrix elements which are between states which are in the same sector, but you need to keep all sectors. This is my point. You do an average over all sectors. And then what we want to do is now to go into each of these sectors individually and understand what is the dynamics there. And this is the way how we get a new integrable model. And some parts of this computation were done already by some other people, but I believe that what this new integrable model is actually only appeared 2 or 3 years ago. But maybe some people in the audience can correct me, but I think it's new, and this is called folded XX model. The name, I can write it down, so folded XX. The name was figured out, was coined by the group of Maurizio Fagotti together with Leonard Zadnik. It refers to some kind of procedure of how they obtain the model. So they claim that they view the spectrum and then they somehow fold it together so that everything becomes at one point. But This is their procedure of getting it. But it's just a name. For us, it's just a name. I don't care about what it means. It's just a name. And remember again that actually, I mean, the classical thing is still there. So if you want the classical Ising model, it is still there, the number of domain walls, as Robert said, and you still have at the very top and very bottom, you still have these extreme cases of Néel and complete ferromagnetic. But in between, you have some non-trivial happening. And now we want to understand this model. So now we want to understand, so to say, what is the effect of perturbation, this perturbation compared to these classical charges, which is the number of domain walls essentially. And then what I said, we want to look at, so to say, matrix elements or transition matrix elements of the Hamiltonian, which lie within a given sector. This means that I want to take those transition matrix elements dictated by the Hamiltonian, which do not change the eigenvalue of Q2, which do not change number of domain walls. I explained to you that this is what we need to do. And let us just draw some, not pictures, but simple computation. So this is in the given basis of spins, this is a diagonal operator, but this gives you hopping terms. So normally, if you have the normal x-exact Hamiltonian, that this gives you hopping terms. So from up down, you can go to down up and vice versa. I mean, this is dictated by x equals epsilon. Maybe you get a coefficient of 2, but it doesn't matter. Now, what happens when we have this requirement that we do not want to change the number of domain walls? We want to keep the number of domain walls fixed. Now, let us play a little game. So let us imagine that we have a hopping amplitude, but this hopping amplitude is not isolated from the rest of the spin chain, but we take also the neighbors into account. So for example, we have a situation where we have here an up spin, here an up spin, here a down spin, and here a down spin. And now we want to do this hopping for the middle sides. Then from this, we would go to up, down, up, down. Now you can see that this should not be allowed because this changes the Q2 eigenvalue. Because here the Q2 eigenvalue was +1, here it's -1, here it's +1. So altogether we have +1. But here the Q2 eigenvalue is -1, -1, -1. So altogether it is -3. So the number of domain walls gets changed. I mean, here we just had a single domain wall. Here we have 3 domain walls. So this should not be allowed. So we say that for our procedure of what we are doing, we throw this matrix element out. We pretend it doesn't exist. Indeed, and no, not indeed, but instead we go further. So we consider a situation which is not like this, but for example, there was up, up, down, and then up. And then we do this hopping here. So from this, we go to up, down, up, and up. And here we see that the number of domain walls is actually conserved. So the Q2 eigenvalue is not changed because here we have plus, here minus, here minus, and here we have minus, minus, and plus. The sum is the same. So this is allowed. And you think a little bit, then you see that there is spin reflection symmetry. So basically, this is the only thing which is allowed. So the only thing which is allowed is that the middle 2 sides can do hopping if the outer 2 sides have the same orientation. And from this, I can write you a new Hamiltonian, and this is the Hamiltonian of the folder XXA model. I will write it down here. This cannot be moved. Okay, so I will delete and write it down here. Folder XXA is given by the Q4 operator. It is a Hamiltonian acting on 4 sides. Summation, there is a summation over J. There is an operator which measures somehow that the outer 2 spins should have the same configuration. I write it as 1 plus z at j plus 3 over 2. Then this makes sure that you only take those things into account, configurations into account where there is the same on the side 1 and 4. And then you multiply it with the hopping terms. So x at j plus 1, x at j plus 1, x at j plus 2, plus y at j plus 1, y at j plus 2. And then this is our Hamiltonian. It's a 4-side Hamiltonian. And now I claim that this is a new Hamiltonian. So to our best knowledge, this Hamiltonian appeared only 2 or 3 years ago, depending on what you look. And actually, I can tell you a story. So it appeared in 3 different papers, actually. And 2 of them didn't know about each other. And we were the 3rd one, actually. And we discovered it also independently. But then somehow we discovered that it is in the literature already 2 times. And then we wrote to all of the authors and etc. etc. So now I think it is fair to say that it appeared in 3 places independently from each other. And it's a new integrable model. And some other limits similar to this were considered in the literature. It is called constrained XXA model of Alcaraz and Bariev, but it's not the same. It's not the same. They have some projection operators. Here it's not a projection operator. We don't have any projection operator. The Hamiltonian acts on the full Hilbert space. This is for the XXA model. So let us then stop for a moment. I will analyze the properties of this model, but let us think a little bit. So what happened? We took an integrable model, we took matrix elements of the Hamiltonian, and we threw some set of matrix elements away. And we said, this is not happening, it's 0. And we kept another set of matrix elements. I mean, then you should ask yourself, is this model integrable or not? Because it's not evident, as far as I can tell, just from this procedure that we did so far, it's not evident that this should be integrable. So what do we know about this model, this given by Q4? I mean, we know definitely that Q4 commutes with this Q1 and it commutes with this Q2. I mean, this is how we constructed it. So it keeps spin, global spin, and it keeps domain ball number. This is how we obtained it. So it commutes, but in order to have an integrable model, you know, we should have a complete tower of conserved charges. So we should have something like a Q3 and also a Q5 and most other charges, which would all commute with this Q4. So question is, does it exist or not? How would you do it? And you can, I tell you the answer, so it exists. So this is an integrable model which has an infinite tower of conserved charges. But the story is very, very interesting, and I would like to talk about it because it's not evident what these charges are actually. So you can sit down and you can play, you can make an ansatz for Q3, Q5, etc., play around and fix the charges, and you will find that they exist. This is one thing that you can do. And actually in the paper of Maurizio Fagotti and Leonard Zagli, this is what they did. So they gave explicit charges for Q3, Q5, and I think that they stopped. Maybe they also had Q6. Instead, what we did a different procedure, and we gave another procedure for finding all charges. What's more, we also gave new Lux operators and new R matrices, which give you this model, and new transfer matrices from which you get all of the conserved charges of this model. And this is a crucial and delicate point, and I would like to explain it. So there are multiple ways of you can view this whole story. I mean, you know that Heisenberg spin chain is derived from 6-vertex model, and 6-vertex model gives you a transfer matrix. From transfer matrix, you derive the charges. This we know very well. And then you can ask yourself, I mean, what happens if I take those charges and send delta to infinity? And what happens with Lux operators? What happens with the transfer matrix? And it just turns out that somehow when you do this limit in a little bit careless way, then most of the things just die out. So most of the interesting charges scale to 0, and Lux operator becomes trivial. So my claim is that in order to get all of the conserved charges here, you cannot do this scaling limit, or not scaling, this limit, you cannot do this limit directly on the 6-vertex model, but you need another structure. And this is perhaps surprising. So I wonder what the audience thinks about it. It was a little bit surprising to us, but actually it is true. So you can play with Lux operator of 6-vertex model and do this limit, but it just becomes some permutation operator or diagonal or something, and you will never get these charges and the higher ones from that. Somehow these come from subleading contributions of this limit of the transfer matrix. Instead, what can we do? So we devised two methods. The first method is a direct method. The other one is the algebraic method. Now, the direct method is the following. Maybe I will now use this blackboard to have a kind of a correspondence. So we look first at finite delta. At finite delta, we know that the model is integrable. It has an infinite tower of conserved charges. So there is a tower of charges Q alpha, where each charge is a global. It's an extensive charge. It spans alpha sites, and alpha goes from 1, 2, 3, etc. to infinity. So one is global magnetization, 2 is Hamiltonian, 3, etc. are higher charges. And we know that they form a commuting set of charges. So Q alpha and Q beta, they commute with each other. This we know, and this holds for every alpha. So no, not sorry. Well, every alpha, beta, and every coupling constant delta. So the charges, they depend explicitly on delta. And it's clear from here that Hamiltonian depends on delta, but Q3 and Q4 also depend on delta. They will be polynomials in delta, so to say. And then we do a trick. So we say that from each charge, Q alpha, we consider the leading term in delta. And then my claim is that if we do this, the leading term in delta, and we get rid of delta, the delta prefactor in the leading term, then we will get a set of charges which still commute, and which will become the charges here. And it's not trivial that these things are the same, because I mean here we develop this Q4 from the Hamiltonian, and now I'm looking at the charges which are the higher charges of the Heisenberg chain. So it's not evident that this is the same, but it will become the same. So for Q1 of the Heisenberg spin chain, we immediately get this Q1 because it remained. There's nothing happening. From Q2 of the Heisenberg spin chain, well, we get this Q2 because leading term in Hamiltonian is this one, and we get rid of the delta. But then we can play the game also for Q3 and Q4. So it turns out that when we look at Q4 of Heisenberg spin chain, it is a four-side operator, which is a polynomial in delta. I don't even remember, was it the first order or second order in delta? Maybe it was second order in delta. So from this polynomial, we need to compute, we need to not compute, but somehow just take the coefficient delta square. I think it was delta square. And then it just turns out that we find this operator. And from this relation that it commutes for every delta, it is clear that the leading term will also commute. And then, well, the leading term gives Q4. And if we'll go for higher charges, Q5, Q6, then we can play the same game. And it is clear from this equation that the leading terms will always commute. And from this procedure, you get an infinite tower of charges for this further X-ray model. Of course, there are some technical difficulties here, some delicate things, because sometimes it happens that the leading charge of the leading coefficient in alpha, leading terms leading terms in delta, they will become the same operator. So I remember that it just happens that for Q5, the leading term will be the same as the leading term in Q3, but then you can subtract it and then look for next leading term, and it still commutes. And you can do this procedure and you get an infinite tower of charges. So that's nice. Then we know that the model is integrable, we know. But maybe you are not satisfied with this, and at least, so we were not satisfied with it because it's still an ugly thing to do. So we want to do some kind of algebraic construction for this model. And this algebraic construction, I mean, we thought a little bit and then we figured out how to do. And actually, it led us to formulation of a little bit new framework for algebraic beta ansatz or quantum inverse scattering approach. So our goal then was to have a formulation, what we call medium range spin chains. So we developed a new formulation with which we can describe Hamiltonians, which are somehow summations over Hamiltonian density J, where Hamiltonian density is not nearest neighbor, but it can have three-side interaction, four-side interaction, maybe even longer interaction. And we looked at these models and we figured out how to make blocks operators for them and air matrices for them. And this is a topic for a separate talk. I mean, last time Robert heard me talking, I gave a talk just about this one. So today I chose to talk about this side of the story. So it's not, I don't have enough time to go into details here. Let me just give a very few remarks. So here for these models, what we call medium range spin chains, we require that it should be translational invariant. Because in the literature, there are some constructions where you can have some staggering, and then it is understood how to build integrable models with staggering. But these models will be actually new, so which is translational invariant, and the charge spans more than two sides is new. And also we require, of course, that the Hamiltonian should be the smallest charge which generates dynamics. What is dynamic generating? So it is where the Hamiltonian is a sum of non-commuting terms. So for example, here, of course, Q4 is not the smallest charge. Here, Q4, I mean, there are smaller charges, Q1 and Q2, but they do not generate dynamics. It is a sum of commuting terms that can be diagonalized easily. Q3 and Q4 are actually the smallest charges which give you dynamics. And we wanted to look at these types of cases when the medium range Hamiltonian is the smallest interesting charge. And then we devised a new formalism for this. Two words for those who know this matrix product operator approaches, etc. So normally when you have a transfer matrix, then maybe I can draw it like this, that you have these boxes which are Lax operators. Again, I don't have time to discuss everything, just a just some pictures I will draw very quickly. So these are physical spaces. This is auxiliary space, and then this is the product of flux operators or R matrices, if you wish. And then this gives you a transfer matrix. Now we have normally you have a spectral parameter here, a U spectral parameter, and then you have a trace in auxiliary space. Roughly this is. And instead, we figured out that in order to have medium range spin chains, we need to increase the auxiliary spaces, but keep this kind of separation in the physical sides. So for example, if we have a free site operator like here for Q3, then we would take a Lux operator which has one physical space and two physical spaces and two auxiliary spaces as input. And these are of the same dimension. And then we would draw transfer matrices like this that I put Lux operators here beside each other. So this means that the auxiliary space is a tensor product space, is a double tensor product. Again, here we take products in auxiliary space and we take a trace in auxiliary space, and these are the physical spins on which the transfer matrix acts. And with this construction, actually, it turns out that you can find these Hamiltonians, and also you can find R matrices which will give you intertwining between these Lux operators. So with this method, we found new R matrices which act on bigger spaces, and typically these R matrices are of non-difference form. And actually, in some cases, I went to people who are more expert in R matrix, catalogs of R matrices, and it turns out that they were either new or they were some special form of some construction which is somehow hidden in some paper that not many people read. It happened, but in any case, in some cases, they are really new R matrices of non-difference form. That's what I wanted to say. But interpretation with respect to algebra, this is not clear at the moment. So for example, I can tell you what is the R matrix for this one. I don't know it by heart, but I can look it up on my laptop. But for the algebra, I don't know what it is. I mean, it's completely open. I can tell you the form. I can tell you why it is like that, but I don't know quantum group interpretation or anything. We just know it exists, and with the R matrix and Lux operators, we can tell you that the model is integrable, but we haven't done much more. So that's the state of art of algebraic integrability. And we have a paper with Tamás Gombor where we discuss this construction in detail. So I will not go into that more. And instead, I want to use the remaining time to discuss some properties of this model in more detail. So physical properties of this Folder X6A model. So I will delete this one because I believe that the physics is also interesting and it gives you a simple beta-ansatz solution. So let us forget the algebraic things because that's complicated. Very interesting, but complicated. Instead, let us simply just look at coordinate beta-ansatz. So we want to do coordinate beta-ansatz for this model. What does it do? How can we describe it? Okay. Now, if you look at these transition matrix elements which are allowed, then you will already see that the simple ideas of coordinate beta-ansatz, it seems they work. So you start with the reference state, which is all spins up, and then you just create excitation. Excitation is the downspin. And then it is placed into a sea of upspins. Then you will see that it moves. So you can get the one particle eigenenergy. It is the same as in the X6 model. And then you can also consider two particle states. So you can consider a situation where you have two downspins, which are separated from each other. And then propagation of two downspins. And then you want to consider two bodies, scattering and two bodies. You can work it out. Let me just say pictorially what happens. What happens is that the two spins, when they propagate, they cannot come close to each other. They cannot occupy neighboring positions. It will be forbidden. So why is it forbidden? Because imagine that there will be a certain time when, for example, the particles come close to each other, when there would be this configuration. And this is all upspin, and they are here. They cannot move here because there is no transition matrix element which would allow it. It would break Q2. It would break the number of domain walls. I mean, here this is same spin, so this transition is not allowed. Also, here this is the same spin, so this transition is not allowed. So they stop here, and afterwards they move back. So it behaves something like a hard rod, basically. So if you compute the S matrix scattering matrix for this coordinate beta-ansatz wave function, it will be the S matrix of the hard rods. So S as a function of P and Q, two momenta in this case, maybe, or quasi-momenta, will be e to the, I forgot whether it's minus or plus here, but maybe it's minus. p minus q. But anyway, it should be defined, and maybe it's plus here. It depends on conventions, etc. But something like this is the scattering matrix, very simple S matrix for this particular scattering process. And with this one, you can build beta ansatz states. But then the question remains, okay, I build beta ansatz states, but then I exclude situations where I would have the two downspins at the same neighboring position. So what happens then? What do we do with those cases? And the answer is that they behave like a second type of particle. It's similar to nesting, but not completely the same as nesting. So I can tell you another situation. What can happen is, consider that you have up, and then just a single domain ball in your system. Maybe it's an infinite system now, or we don't care about periodic boundary conditions. So you have this. Now this configuration is completely frozen in this model, because here nothing happens, here nothing happens. And normally you would have some kind of like dispersion of spins here in the middle. But here in the middle, these two cannot move because they are different spins. Just a simple transition matrix element would break again Q2 number of domain balls. So this is a frozen configuration, and then it stays in the spectrum. Actually, it turns out that whenever you have two downspins or three downspins, it's also a frozen configuration. It will not evolve at all. There will be many frozen configurations in the system. And then you can also ask the question, okay, but what happens if I just send another downspin to the frozen configuration? So I have here a vacuum, which is all upspin. I send the single particle. I send this single particle to this domain ball. What happens? It is domain ball. Here is again frozen. Now it just turns out that when this particle comes close, it does not break the domain ball, but actually it will enter this area as a whole. So you can play with it, but this is what will happen. So when just imagine that this particle comes close, there will be a situation where here we have upspin, here down. Now a single upspin remains, and this is down, 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 etc., down, down, down. Now here, this cannot move further because these two are different, so this cannot move here. But when you look at this transition matrix element, suddenly this becomes possible, because here you have two downspins, and then this transition becomes possible. So afterwards, what can happen is that this will move to down, down, and then here is an up, and there is a down, down, down. And then this excitation can then move further. And then eventually what will happen is that here the excitation was a downspin placed into a vacuum of upspins. Here it becomes a it becomes an upspin placed into a vacuum of downspin. And then as a whole it travels. So energy and momentum is conserved, but spin in this respect is not conserved locally, but globally it is conserved. And what happens is that as an effect, you can see here that let me show it to you. The domain ball boundary gets displaced. So here was the domain ball boundary, and afterward the domain ball boundary is moved here. So the full domain ball is displaced by 2. And this is how we conserve the global spin. And we also conserve the global domain ball number. And then you can write down a beta ansatz actually for having some number of domain balls and some number of single particle excitations, two types of particles. You figure out what is the S matrix between these two types of particles, and then you can write down your beta ansatz wave function in the most general case. And it's a complete. And here you can prove completeness of beta ansatz because it's a special theory. And let me come back to this original idea of Heisenberg spin chain. Remember that the spectrum here is very complicated, because if you have delta bigger than 1, you have all types of strings in your system. All beta ansatz strings are allowed. So this means that it's a very complicated beta ansatz. All string scatterings should be computed, etc., etc. But in this limit, when we look at it in a good way, the whole thing simplifies. So from all of the strings, you just get two types of particles eventually in a good description. The good description tells you two particles, a single excitation, and the domain ball. But it's also important that a single excitation can change the orientation depending on where it is. So here, a single excitation was downspin, but when it moves here, it becomes an upspin. So it is transmutated if you want. So that's an interesting physical effect. Okay, I should write down what is the beta ansatz scattering factor for this, but it is something like this with the 2, but I would mess up now the plus and minus sign, so I will not get there. Yeah, and we are close to the end of my talk. Maybe I should now at the end also tell you something about the infinite coupling limit of Hubbard. I don't know if I have enough time to go there because it's maybe 7 minutes remaining, or even less, 5 minutes remaining. So it just turns out that maybe it's crazy. It just turns out that this model is actually equivalent to the infinite coupling limit of Hubbard if you do a non-local transformation. So I don't know if this is surprising to people or not. I mean, there are many connections between different models, but when we first understood it, it was a little bit surprising to us. Because Hubbard model is a model with local Hilbert space, which is 4-dimensional. There are 4 possibilities locally. This is a model with 2 local possibilities. And then a relation between the two is, you would think it's very difficult to find it. But actually it is possible in this maybe crazy or special limits. So I can write it here maybe, or so in the Hubbard model, you know that you have 4 states locally. You have the empty state, or you have single electron states, up electron or down electron, or on the same side you can put up and down, and usually it is denoted like this. So this means it's on a single side, but 2 electrons of different spin are placed on the single side. So this is a 4-side model, Hubbard model, and you can get Hamiltonian for it. And then in this Hamiltonian, well, I will not write it down. I hope you remember it as a coupling constant U, which describes you potential energy associated with this configuration. Now you can also send this U to infinity, and then you can do a limit, which is not the same as here. You can do a limit where you do it in a more standard way. So you go from U to infinity, and basically you throw out this configuration. Because then you say that this has infinite potential energy. So it's not the same thing what we did here, because that's special. Here you would want to do U is bigger than temperature, and then maybe this is bigger than 1, or maybe temperature can be order 1. So you really throw out these kind of configurations. Then you get a Hilbert space, which is 3-dimensional. And this Hilbert space is also called, sometimes it's called, model is called a T0 model. And in the bosonic version, spin chain version, it is called Massarani-Mathieu spin chain. If you want, I will write it. Well, I will write it down. So it has 2 R's. Massarani, maybe this way. Massarani-Mathieu model. It is also called the SU3 version of XXX model. So maybe it's a stupid name, but anyway, it's called like this, SU3 XXX. And in this model, what happens is that on the top of the vacuum, you can propagation of upspin and downspin, but they cannot exchange order. Because in this model, actually, so normally in Hubbard model, you have propagation of upspin, downspin with some potential energy, but this configuration is forbidden. So if you have a configuration like this, where you have a neighboring sites, an upspin and downspin, they cannot exchange place because the propagation term in the Hubbard Hamiltonian just would move 1 particle. So it would move from this to 0 and then up, down, or maybe it would move this here, then we would get up, down, 0. But this is forbidden because we threw this out. So this is forbidden, this is forbidden. So from here, you cannot go to down. So this means that in this special model, the spatial order of down and up is preserved. They can move, but it is preserved. It is pattern conserving, if you want. And then maybe it's not, I mean, I'm just out of time, but I can tell you that if you analyze the domain ball pattern in this model, so domain ball pattern here, then you can actually identify 3 types of states such that the Hamiltonian for this model can be just transformed this T to this T0 model Hamiltonian, which preserves spatial ordering. And then it becomes, local space becomes 3-dimensional because the non-local mapping that we do, it actually changes the volume depending on the configuration. So it's a very non-local mapping such that it is even volume changing. I mean, I don't have time now, maybe in the break or something, I can explain it if somebody interested, but such a thing exists. And it also tells us that somehow the algebraic structure of these 2 models is, in this limit, it's related. Otherwise, it's not related, but in this limit, it's related. And there's also a story about Hilbert space fragmentation, but I don't have time for that. So I think I will end it.
Thank you. You mentioned that the R matrix for Q4, you know it.
Sorry?
You mentioned that the R matrix for Q4, you know it.
Yeah.
Right. So how did you get it? Is it from the XXZ R matrix or
no?
Not possible? Okay.
No. We made guesses. So So we used some tricks of the XX spin chain. So well, not tricks, but some input from the XX spin chain. So we looked at what is the R matrix for XX model. Well, this is well known. 6-vertex model has a special choice, so it has coarse and thin, etc. But now the R matrix for this one is bigger because of this doubling of Hubbard states. So R matrix of XX model is of size 4 times 4. But now we have this doubling, so our R matrix is of size 16 times 16 actually. And then we just have very similar matrix elements arranged in a different way. So that and supplied with some. So somehow this structure should be there in the R matrix. So because this dictates you something with XX model, but then this should be also there. So it gives you some selection of which matrix elements are non-zero, etc.
Okay. So I have another question. So you spoke about this folded XXZ. What about the folded open XXZ?
Huh?
What about the folded open XXZ?
I mean, we haven't looked.
Yeah, because the boundary parameters, do they enter also in the how they enter? Okay.
I mean, it shouldn't be so difficult, but so what happens? I mean, domain wall should be also conserved. So, I mean, you can do two things. I mean, either you do this derivation of the limit, or you just say that this is your Hamiltonian, and then you choose boundary conditions new. I don't know what is.
But this the Q4 is obtained from the. So that's the obtained from the expansion of the transfer matrix and taking the limit. Of, okay, of XXZ for delta goes to infinity, right? So if you do the same for,
you should
the open, then you will get the open folder. Okay.
Yeah.
It's just about the bound.
But maybe it's actually so we haven't even. So for example, this comes from Q4 of normal Heisenberg. So maybe Q4 of Heisenberg for the boundary terms, it's not just one side, but it has maybe two side things. I don't know. So it might be that boundary condition here is even more complicated. It's a good question. We haven't looked.
Yeah, so your S matrix is very simple. So that means your beta ansatz equations are very simple. Can you solve for the beta roots?
Yeah.
Exactly.
Very good question. So yes, you can. So this means that when you have a beta ansatz, so that's the whole point of the model. That in models like this, you can derive results for real-time evolution because you can solve beta ansatz equations analytically.
For all eigenstates.
Yeah.
Okay, and then your model, it's
explicitly parameterized, but somehow, so when you think about beta equations, maybe I can write them down. An S matrix like this will give you a rescaling of the volume or change of the volume. Because, normally on beta ansatz equation, you have e to the I pi L multiplied by all other, I don't know, S P minus K, and then you have a product over K. But when you do this is the S matrix, then somehow these factors can be collected here and they change this volume. And then the other factors can also be collected. It will give you something like a total momentum. So you have a selection to total momentum sectors. And afterwards, you just have almost free, but with a changed volume. So this is essentially hard rod. So we have another paper where we also call it hard rod deformation of XXA. We can actually add some interaction further terms to this. But basically particles behave like as if they would be a hard rod, so have the size, and then available volume is changed.
And so in the end, you can compute the eigenvalues of the transfer matrix, and it has a gap, right? So the difference between the leading eigenvalues, if you take the ratio and you take the system size to grow, it does not converge to 1. The ratio of the two largest eigenvalues.
I don't know why should it be gapped? I mean, in the thermodynamic limit, I think this is also gapless.
I think gapped because if usual XXZ is usually gapped when you're outside of -1 to 1, and then you're taking the limit to.
Yeah, but this no. But this gap that you were talk about is somehow the gap between in the original picture where you had just the ferromagnetic state, and then this is your gap. But then we forget about this because now we look at the small differences within each sector. Actually, it will become gapless. Okay. It's strange, but
can I come back to your R matrix? You say you go from 4 by 4 to 16 by 16. Yeah. There's some coupling of the initial R matrix because it's the same kind of R matrix you can talk about. You start from XX, and then you couple in some way complicated with the XX, and you end up with a 16 by 16 matrix.
So it is something similar, but we don't have precisely the same type of arrangement. So it's open. I really invite people to look into our formulas, and maybe somebody could figure out algebraic interpretation. Because what we did is we did this geometric arrangement of which matrix elements are non-zero and which are zero based on what is here, and it works. And the interpretation is different from Hubbard because we don't have a doubling of chain. We have something different. But of course, the feeling is very close. So, and I can tell you that I mean, this my friend of mine, Andriy Liashik, he's looking into it, but he hasn't published. So he has an interpretation of our air matrix in terms of some of air matrix, which is known in some paper somewhere. But I don't know. I mean, he hasn't published yet. So.
Okay, no other questions. So let's speak the speaker again.
Excuse me, can I ask the question?
So it was the last talk of